September 12, 1944. Kummersdorf Proving Ground, Germany. 10 and 20 hours, Oberingenieur Heinrich Ernst, 38, chief automotive engineer at the Wehrmacht testing facility, watched as technicians disassembled a captured American M4 Sherman tank. His assignment was to evaluate Sherman mechanical systems and report on any technologies Germany should adopt. Ernst had examined dozens of Allied vehicles. Most were unremarkable mechanically. But he'd heard persistent reports from the Eastern and Western fronts about Sherman reliability. American tanks broke down far less frequently than German tanks. This seemed impossible. German engineering was superior. Everyone knew this. The Panther tank was a masterpiece of automotive design. The Tiger was mechanically sophisticated. How could crude American tanks be more reliable? The Sherman's transmission was removed and placed on the examination table. Ernst inspected it carefully. The design was simple, almost primitive by German standards. Single-stage gearbox, straightforward synchromesh, basic materials, nothing sophisticated, nothing that demonstrated advanced engineering. But as Ernst studied maintenance records from the captured tank, he understood something his colleagues had missed. This simple transmission lasted 3,000 kilometers between major maintenance. The Panther's sophisticated transmission often failed within 150 kilometers. The Tiger's transmission rarely exceeded 1,000 kilometers. The correlation was undeniable. Simple worked. Complex failed. What Ernst concluded in his report would challenge fundamental assumptions of German engineering philosophy and show that in war, reliability beats sophistication every time. By September 1944, German armored forces faced a mechanical crisis that was destroying combat effectiveness as thoroughly as Allied firepower. The Panther tank, introduced in 1943 as Germany's answer to Soviet T-34s, was mechanically unreliable to the point of being tactically useless in many situations. Final drives, the gearing connecting transmission to tracks, failed catastrophically with depressing regularity. Transmissions broke, engines overheated, suspensions collapsed. On paper, the Panther was formidable. 75mm high-velocity gun, sloped armor, decent mobility. In practice, Panther units often had 30 to 40% of their tanks non-operational due to mechanical failure. Not combat damage, mechanical failure. Tanks abandoned on roadside because final drives broke. Tanks immobilized because transmissions jammed. Tanks unable to move because engines failed. The Tiger tank, even more sophisticated and powerful, had similar problems. Its complex overlapping road wheel suspension was prone to freezing in winter. Its transmission was delicate and prone to failure. Its engine required constant maintenance. Tiger units rarely had more than 50% operational readiness. Again, not from combat but from mechanical problems. The Sherman tank was mechanically simple by comparison. Its Continental R975 radial engine was derived from aircraft engines, proven and reliable. Its transmission was straightforward in design. Its suspension, while not sophisticated, was robust and maintainable. The entire vehicle was designed for mass production and field maintenance by crews with moderate mechanical training. German tanks were designed by engineers pursuing technical excellence. Every system was optimized for maximum performance. The Panther's transmission used high-quality steel gears machined to precise tolerances. The final drives used complex planetary gearing to maximize power transfer efficiently. On paper, these designs were superior to Sherman's simpler systems. In practice, they broke constantly. The fundamental problem was that German designs operated at the limits of material capabilities and manufacturing tolerances. When materials weren't perfect, when manufacturing wasn't precise, when maintenance wasn't thorough, systems failed. And in wartime conditions, materials were often substandard, manufacturing was rushed, and maintenance was performed under combat conditions by exhausted crews with limited time. Sherman designs included substantial safety margins. Components were stronger than strictly necessary. Tolerances were looser than optimal performance required. Materials were standardized rather than optimized. This made Shermans less efficient than theoretically possible, but it made them far more reliable under real-world conditions. Oberingenieur Ernst's report, dated September 25, 1944, and recovered from German archives after the war, documented his findings clinically. American M4 Sherman tank demonstrates design philosophy fundamentally different from German practice. American designers prioritized reliability and maintainability over maximum performance. Transmission uses simple single-stage gearing with generous tolerances. Materials are standard carbon steels without special alloys. Construction allows field maintenance by personnel with moderate training. The result is a transmission that functions reliably for 3,000 to 4,000 kilometers between overhauls under combat conditions. The report continued with comparison to German designs. Panther transmission uses sophisticated dual-stage gearing, requiring precision manufacturing and high-quality materials. Under ideal conditions, this design provides excellent performance and efficiency. Under combat conditions with suboptimal materials and rushed manufacturing, reliability is poor. Field maintenance requires specialized training and tools often unavailable at unit level. Average service life is 150 to 300 kilometers before failure. This difference in reliability has greater tactical impact than theoretical performance advantages. Ernst's conclusion was professionally devastating to German engineering pride. American approach of simple, robust design with generous safety margins produces more tactically effective vehicles than German approach of sophisticated design operating at performance limits. Recommendation is to adopt American design philosophy for future vehicle development. However, this recommendation likely cannot be implemented given current industrial situation and time constraints. The final sentence acknowledged reality. By September 1944, Germany lacked time, resources, and industrial capacity to redesign vehicles, retool factories, and produce new vehicles in meaningful quantities. German armored forces would continue using Panthers and Tigers, despite mechanical unreliability because alternatives didn't exist. The mechanical reliability difference translated directly to tactical effectiveness. An American armored division with 200 Shermans typically had 180 operational on any given day. A German panzer division with 100 Panthers typically had 60 to 70 operational. This meant American divisions maintained numerical superiority even when German tanks were technically superior on a one-to-one basis. Numbers mattered more than individual quality when the numerically inferior force also had lower operational readiness. The logistical impact was equally significant. Sherman mechanical simplicity meant fewer spare parts required, less maintenance time needed, easier field repairs. Panther mechanical complexity meant extensive spare parts inventory, longer maintenance procedures, frequent need for depot-level repairs unavailable in field conditions. American logistics could support Sherman operations sustainably. German logistics struggled to keep Panthers operational despite heroic efforts. German tank crews lived with chronic mechanical unreliability that affected morale and tactical planning. Lieutenant Otto Carius, a Tiger tank commander who survived the war and wrote memoirs, described the mechanical problems candidly. Our Tigers were mechanically temperamental. Drivers needed extensive training to operate the complicated controls properly. Even with good drivers, engines and transmissions failed regularly. We became accustomed to tanks breaking down during marches. Abandoning tanks due to mechanical failure was routine. This was frustrating and demoralizing. We'd destroy our own tanks to prevent capture, not because enemy action but because we couldn't repair them. Carius contrasted this with American tanks. We captured several Shermans during various actions. Our mechanics examined them with interest. The consensus was that American tanks were mechanically crude but reliable. Any German tank driver could operate a Sherman after 10 minutes familiarization. Any mechanic could repair one with basic tools. This was completely different from Tigers, which required specialized training and tools for even routine maintenance. We understood that American simplicity was actually superiority in disguise. The design philosophy difference reflected broader cultural differences in engineering. German engineering culture valued sophisticated solutions demonstrating technical mastery. Elegance and efficiency were prized. The Panther's transmission was elegant, It was efficient. It was sophisticated. It was unreliable. American engineering culture valued practical solutions that worked reliably. Elegance mattered less than function. Efficiency mattered less than durability. The Sherman's transmission was practical. It was durable. It was reliable. This cultural difference manifested in countless design details. German tanks used complex systems where simple systems sufficed. Overlapping road wheels provided smooth ride but were maintenance nightmares. American tanks used simple bogie suspensions that were rougher but robust. German tanks used sophisticated gearboxes maximizing power transfer. American tanks used straightforward transmissions that were less efficient but rarely broke. The cumulative effect of hundreds of such choices meant German tanks spent more time broken than American tanks. The manufacturing implications were substantial. Sherman transmissions could be produced by facilities with moderate precision machinery and average skilled workers. Panther transmissions required precision machinery and highly skilled workers. As Allied bombing degraded German industrial capacity and skilled workers were drafted for military service, maintaining production quality became impossible. Late-war Panthers had even worse reliability than early models because manufacturing quality deteriorated while designs remained. Demanding American industrial capacity allowed production of spare parts in vast quantities. Sherman crews received replacement transmissions, engines, and major components readily. Field maintenance could replace entire assemblies quickly rather than attempting complex repairs. German forces often lacked spare parts entirely. When components failed, tanks were abandoned or cannibalized for parts to keep other tanks operational. The operational readiness statistics demonstrated this disparity quantitatively. U.S. Army records from 1944 show Sherman operational readiness averaged 85 to 90% across armored divisions in Europe. German records show Panther operational readiness averaged 50 to 65% for divisions in active combat zones. Tiger operational readiness was typically 40 to 50%. This meant American armored units could commit nearly all their tanks to operations, while German units always operated with significant portions of their strength non-operational. After the war, German tank designers and engineers acknowledged American design philosophy was superior for wartime conditions. Oberingenieur Ernst continued working in automotive engineering in post-war West Germany. In a 1965 interview, he reflected on his Sherman transmission examination. At the time, I was shocked by how crude the Sherman transmission appeared. It violated every principle of elegant engineering I'd learned. But as I analyzed its reliability and considered operational requirements, I understood that American engineers designed for reality while we designed for theory. In reality, tanks operate in mud, dust, extreme temperatures, by exhausted crews under combat stress. Simple, robust designs survive these conditions. Sophisticated, elegant designs fail. This lesson influenced German automotive engineering profoundly after the war. Modern German vehicles are reliable because we learned simplicity and robustness from studying American designs. The Sherman wasn't without flaws. Its armor was inadequate against German tank guns by 1944. Its main gun was less powerful than German weapons. In one-on-one engagements, Panthers and Tigers could destroy Shermans easily. But Sherman mechanical reliability meant there were always more Shermans available. And tanks don't fight in isolation. They fight as units, supported by logistics, maintained by crews, operating continuously over weeks and months. In sustained operations, reliable adequate tanks beat sophisticated unreliable tanks. Modern military vehicle design incorporates lessons from Sherman versus Panther comparison explicitly. The U.S. Army's design philosophy emphasizes reliability, maintainability, and operational readiness over maximum theoretical performance. Specifications include reliability requirements measured in mean miles between failures. Designs must be maintainable by soldiers with specified training levels using equipment available in field conditions. These requirements derive directly from World War II experiences when American reliability defeated German sophistication. At the National Armor and Cavalry Heritage Foundation Museum in Fort Benning, Georgia, a Sherman tank is displayed next to a Panther tank. Technical specifications comparing both vehicles show the Panther as superior in armor, armament, and mobility. But a second placard shows operational readiness statistics demonstrating Sherman's superiority in availability and reliability. The exhibit explains that tactical effectiveness combines vehicle performance with operational availability. The best tank that's broken is less effective than an adequate tank that's operational. A teaching principle at military engineering schools states, "Reliability is a performance parameter." This means reliability shouldn't be considered separately from speed, armor, or firepower. Reliability determines whether other performance parameters matter. A tank that's too broken to fight has zero combat effectiveness, regardless of its theoretical capabilities. This principle is obvious now. It wasn't obvious to German engineers in 1942 when designing Panthers and Tigers for maximum performance. The human experience of dealing with unreliable equipment affected German tank crews psychologically. They developed mistrust of their own vehicles. Experienced crews learned to baby their tanks, operating below maximum capability to reduce mechanical stress and extend component life. This degraded combat effectiveness but was necessary to keep tanks operational longer. American crews trusted their Shermans to operate reliably when pushed hard. This trust enabled more aggressive tactics. The broader lesson extends beyond tanks to any engineered system operating under stress. Designs optimized for maximum performance under ideal conditions often fail under real-world stress. Designs with safety margins, simpler construction, and robust components function reliably under stress despite lower theoretical performance. In competitive situations, reliable adequate performance beats optimal unreliable performance consistently. German engineering excellence was real. German engineers created sophisticated designs demonstrating technical mastery. But they designed for perfect conditions that didn't exist in wartime. American engineers designed for imperfect conditions that did exist. The American approach proved superior not because American engineers were better technically, but because they understood operational requirements better and designed for reality rather than theory. In September 1944, Oberingenieur Ernst understood this when examining that Sherman transmission. He saw its simplicity and recognized it as strength rather than weakness. His report recommended adopting American design philosophy. The recommendation came too late to matter for Germany, but it influenced post-war engineering philosophy profoundly. Sometimes the best design isn't the most sophisticated. Sometimes the best design is the one that works reliably when everything else is falling apart. That was the Sherman's secret. Not sophisticated engineering. Reliable engineering, not elegant design. Robust design, not maximum performance. Adequate performance sustained over time. These qualities won tank battles more surely than perfect performance that broke down constantly. German tank engineers examined captured Sherman transmissions and found them crude. They were right. They also found them reliable. That mattered more. In war, reliable beats sophisticated. Every time,